The universe is filled with mysteries, and black holes are among the most enigmatic phenomena. These cosmic objects, born from the death throes of massive stars, warp space and time in ways that challenge our understanding of the cosmos. Misconceptions about black holes, time travel, and dimensions abound, often fueled by science fiction and popular culture. In this exploration, we embark on a journey to demystify these celestial objects, separating fact from fiction and presenting the scientific truths behind these captivating cosmic entities. Contrary to popular belief, black holes are not the cosmic vacuum cleaners of science fiction, nor are they as simple as their name might suggest. They are anything but empty voids. In fact, they are regions of space-time where gravity is so strong that nothing, not even light, can escape their grasp. Imagine, if you will, the most massive objects in the universe concentrated into an infinitely small point. That's the singularity at the heart of a black hole. The event horizon, often described as the point of no return, marks the boundary beyond which escape from the black hole's gravitational pull is impossible. But here's where the misconception lies. Black holes are not entirely invisible. While the black hole itself does not emit light, the area surrounding it can be extremely bright. Picture this: a swirling disk of gas and dust, called an accretion disk, spirals around the black hole, like water circling a drain. As this material falls inward, it heats up to extreme temperatures, emitting radiation across the electromagnetic spectrum, from radio waves to X-rays. This radiation can be detected, as evidenced by the groundbreaking images from the Event Horizon Telescope, which captured the first-ever silhouette of a supermassive black hole in the galaxy M87. These observations have revolutionized our understanding of black holes, confirming their existence beyond any doubt and providing invaluable insights into the nature of gravity in its most extreme form. So, while the black hole itself remains shrouded in darkness, its surroundings tell a different story, a story of intense energy, swirling matter, and the relentless pull of gravity. Just as stars come in a variety of sizes and masses, so too do black holes. They are not a one-size-fits-all phenomenon. In fact, they can be classified into three main categories based on their mass: stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes, as their name suggests, are formed from the collapse of massive stars. Imagine a star much more massive than our Sun, at least 8 times its mass, reaching the end of its life. Having exhausted its nuclear fuel, the star can no longer support itself against its own gravity. The core collapses in on itself, and if the star is massive enough, this collapse continues unabated, forming a singularity, a point of infinite density. Intermediate mass black holes, as their name implies, fall between stellar mass black holes and supermassive black holes in terms of their mass. They are thought to form through the merger of smaller black holes or through the runaway collapse of massive stars in dense stellar clusters. These elusive objects are still not fully understood, but their discovery has provided important clues about the growth and evolution of black holes. Supermassive black holes, the true behemoths of the cosmos, reside at the centers of most galaxies, including our own Milky Way. These gravitational giants can have millions or even billions of times the mass of our Sun. Their origin remains a subject of active research, but it is thought that they grow by accreting matter from their surroundings and by merging with other black holes over billions of years. One of the most pervasive myths about black holes is that they act like cosmic vacuum cleaners, sucking everything in their vicinity. In reality, black holes exert gravitational forces just like any other object with mass. It's the same force that keeps our feet planted on the Earth, and the Earth in orbit around the Sun. Imagine a black hole as a bowling ball sitting on a trampoline. The trampoline represents space-time, and the bowling ball's weight creates a dip in the fabric. Objects placed on the trampoline will move towards the bowling ball, not because it's sucking them in, but because they are following the curvature of the trampoline. Similarly, objects near a black hole are affected by the curvature of space-time caused by its mass. If an object gets too close, it will indeed be pulled in, just like a marble rolling too close to the bowling ball. However, if an object is far enough away, it can orbit the black hole just like planets orbit the Sun. It's all about distance and velocity. In fact, there are stars orbiting the supermassive black hole at the center of our Milky Way galaxy, known as Sagittarius A*. These stars are moving at incredible speeds, millions of kilometers per hour, but they are far enough away that they are not being pulled into the black hole. The event horizon of a black hole is often described as a point of no return, a boundary beyond which nothing, not even light, can escape. This is because the gravitational pull within the event horizon is so strong that it overcomes the speed of light itself. Imagine trying to throw a ball upwards while standing on the surface of a planet with incredibly strong gravity. No matter how hard you throw the ball, it will always fall back down. Now imagine that the gravity is so strong that even light, the fastest thing in the universe, cannot escape its pull. That's the situation at the event horizon of a black hole. Once matter crosses this boundary, it is destined to fall towards the singularity at the center of the black hole. It's not that the matter is destroyed, but rather, it is compressed and incorporated into the singularity, adding to the black hole's mass, and further increasing its gravitational pull. So contrary to some science fiction stories, matter that falls into a black hole does not reappear elsewhere in the universe. It is gone from our observable universe, forever trapped within the event horizon. The idea of falling into a black hole is the stuff of nightmares, often depicted in science fiction as a quick and gruesome demise. While it's true that falling into a black hole would likely be fatal, the experience might not be as instantaneous as often portrayed. Let's imagine for a moment that we could survive a journey into a black hole. As we approach the event horizon, we would experience the strange effects of time dilation. Time would slow down for us relative to observers watching from a safe distance. To them, we would appear to freeze at the event horizon, our image red-shifted into oblivion. However, from our perspective, time would continue to flow normally. We would cross the event horizon and continue our inward journey towards the singularity. As we fall deeper into the black hole, we would experience spaghettification. This is not a culinary term, but rather a consequence of the extreme tidal forces at play. Imagine our bodies being stretched like spaghetti dough, our heads and feet experiencing vastly different gravitational pulls. This stretching would become more and more extreme as we approach the singularity, eventually tearing us apart at the molecular level. The exact details of our demise would depend on the size of the black hole. Larger black holes have gentler tidal forces at their event horizons, meaning we might survive for longer before being spaghettified. When we gaze up at the night sky, we see a tapestry of stars, each at a different stage of its life cycle. Some are young and vibrant, while others are nearing the end of their stellar evolution. It's natural to wonder, do all stars eventually become black holes? The answer, thankfully, is no. Only massive stars, those significantly larger than our sun, have the gravitational clout to collapse into black holes. Our sun, for example, will not become a black hole. It simply doesn't have enough mass. Stars like our sun will eventually exhaust their nuclear fuel, causing them to expand into red giants. These stellar giants will then shed their outer layers, leaving behind a dense core known as a white dwarf. White dwarfs are incredibly dense objects about the size of Earth but with a mass comparable to the sun. However, for stars much more massive than our sun, the story is different. Once these stellar giants exhaust their nuclear fuel, their cores collapse under their own gravity. If the core is massive enough, the collapse continues unabated, forming a black hole. Black holes, once relegated to the realm of science fiction, are now firmly established as real and awe-inspiring phenomena in our universe. By understanding the truths behind these cosmic entities, we gain a deeper appreciation for the complexity and wonder of the cosmos. As we continue to explore the universe, armed with the power of scientific inquiry, we can shed light on these mysteries, unraveling the secrets of black holes and expanding our understanding of the nature of reality itself. The journey to comprehend black holes is far from over. In fact, it has just begun. With each new observation, each theoretical breakthrough, we come closer to grasping the true nature of these enigmatic objects, pushing the boundaries of human knowledge and inspiring generations to come.